Hey everyone, this is Andy Malbuff, and in this video we're going to take a look at how we can use Computation Layer with Activity Builder to put some pretty cool animation in place for mathematical situations involving motion, and in this case, quadratic motion. I want to give a big shout out to Kurt Salisbury. I found this activity he posted in Twitter a while back that put in this animation for quadratics. And I was like, oh, this is awesome. I made a copy of it and fell in love with it. And I'm tinkering around and editing with it. And so I just want to show you some of the cool features of this animation. Well, to begin with, what does animation look like? So I'm going to show you a student screen preview here. And this is a graph component. And you'll notice here there's a little play button in the middle as well as one down here. These are both the same button connected to the same thing. If I press this, it starts a timer, and you can see we're modeling free fall. Okay, and this particular object, modeling free fall, fell for 6.3 seconds. Again, we can watch it again multiple times. Students manipulating can drag this by hand and see various points of the animation. And so this is really cool visually for showing the relationship that as objects are in free fall, the distance between them each second increases due to acceleration. So what does this look like in the back part of this? How do we produce something like this? So I'm going to exit the preview mode and take you into a slide here that's got basically three components. It's got a text input here for student response. It's got a note with directions, and everything else happens in this graph component. First of all, I want to take you into the computation layer because there's very little there. But this is the heart and soul of the animation. There's a sync called animation duration. That sync basically says, we're going to animate this graph. We're going to let it run for a certain amount of time. In our case, 6.3 seconds. Why is it 6.3 seconds? That has to do with a little bit of prep work that I had to do in advance to figure out how long this object is going to be in free fall before it hits the ground. And I'll show you that in just a little bit. I'm also going to define a number, t sub 0. And that number is going to be based upon the animation button being pressed. So t sub 0 is going to start out at 0, and when the button's pressed, it's going to advance counting by ones each time. So our computation layer is not very sophisticated at all, pretty simple. The graph does have a little bit of busyness to it, so I want to talk to you about some of the features in here. Now, the first thing I have in here is the image of a building that we're simulating an object being dropped off the side, if you will. I just found this image online, made a copy, uploaded it here. I mean, pretty simple there, but I did have to manipulate it to change its center point, to change its width and height. Let me elaborate. In my settings, I've turned off my axis numbers. When I turn them on, you'll see here are my x-axis numbers, but I've also turned off my y-axis. And I've turned that off because I want the x-axis to simulate the ground, and I don't need to see any numbers there. And I don't want my y-axis viewing. So I had to manipulate this image so that it looked like it's a building at a height of 600, because I want to simulate this object falling from a height of 600. So I predetermined that's my initial height. And in my function over here, I'm going to set it up that way. 600 is my initial height, and anything in free fall is going to have a quadratic term that looks like minus 16x squared or minus 16t squared. Well, you'll notice here I've not used x or t, I've used t sub 0. T sub 0 is that number we're defining in the computation layer, and I've got it added here as a slider so I can show you manually as t advances, you can see that animated motion. Okay, so I'm going to take it back to 0. So back to the building, you may have to adjust where the center point is. Right now, here's my center point roughly. It's at 2,298. And then you have to tinker around with the width and the height to get that to fit where you want it to go. So I'm going to turn the axis numbers off and the y-axis off, so I'm back to this situation where it looks like it's hitting the ground. Below box 3, below my slider there, I've got probably my most important point that's going to show up. This is my viewing window, if you will. It's got an x coordinate of 10, and the reason it's an x coordinate of 10, everything's going to fall right here. Everything, all of these points are going to have x values of 10. Oops, I didn't mean to exit out of there. The y coordinate is going to come from the function that I'm using, f of x, but I'm putting a domain restriction. Once the t has reached 6.124, once the objects hit the ground, this is not going to show anymore. And then you'll see below that a series of other points. They all have something in common. They all have 10 in common. So they're all going to stack up vertically right here. Well, they all have conditions with them, or domain restrictions. So this first one isn't going to happen until t is advanced to 1. Well, what's this 584? Where does that come from? That's that prep work I mentioned. So I'm going to exit this screen and pop into regular Desmos for a second. And we're going to I'm going to redo this here. We're going to type in the function we want to use. So in this case, I want to use 600 minus 16 squared. And so we get a parabola. I had already had this window open, so I didn't have to adjust any views here. But what's important for me to see is, here's my initial height. This means after 0 seconds, the object's at a height of 600. Well, and I'm going to have various other heights as it goes into free fall. Once it hit the ground, that's a critical point, 6.124. So I want to create a table to get some other height values in between here. So I click on plus to add a table, and I want to have times starting at 0 and advancing up through 6.124. And then for my y coordinates, I want to pull from the function when my x coordinates are inserted in there. So when I make my y coordinates f of x sub 1, I'll see these various values. Let me go ahead and click on them on the graph so you can just see these numbers. These are the various heights at the various times involved with free fall. So circling this point right here, I guess the label went away when I do that. After 3 seconds of free fall, it's 456 feet up. After 4 seconds of free fall, it's 344, etc. So those values from the table are what I'm going to use over here back in Activity Builder as my ordered pair y coordinates. 584, 536, 436, 456, etc. Okay, so those are all those values right there. And that basically produces those solid points as the viewing circle passes by with certain amounts of time. So I welcome you to go ahead and copy or make something of your own like this, play around with it, see what you think about that part. But that is the simplest part of adding animation. If you think that's cool, let's go ahead and add some other stuff in here to connect for students visually. So I'm going to take you to this next slide. And this first component, that's the exact same thing I just had on the previous screen, but I've added another graph here. So let's see what it looks like in preview mode. When I start the animation, the object falls here, but we also get a graph produced on the right-hand side, something really cool so that the kids can hopefully start to see this connection that every second of free fall, the distance between those points is increasing. And I think that's a really cool thing to see. So how do we build that? Well, in my graph component on the left, everything here is the same except I just made all the points black. Nothing other than that. So I'm going to turn that off. But I did label this now. I'm going to call it graph number 2 because I want to take graph number 2's t sub 0 and send it over here. Let me show you what I'm referring to. In the computation layer here, I'm going to define t sub 0 for this component to come from graph number 2. It's t sub 0. So the button over here is going to influence both of these graphs. That's what that essentially means. Inside of the component itself, here's my function that I want to simulate. I've made it a dashed line, and I've given it a restriction. I only want to see positive, the positive part of it, and it's going to go until the timer gets to, it's basically going to be based on the timer. Well, here, let me back this timer up so you can see it in motion. If the timer starts at 0, this is what the students will see, and when the animation button is pressed, they start to see this motion. Now, the timer right now is at 2.5, so they only see points with x coordinates less than 2, which is great. If they want to see the next one, they have to let the timer run past 3. So this part over here is very similar to what we just saw on the previous screen. But this graph component is tied into the first one due to that animation feature. And lastly, we can do a little bit of more connecting work here. You're looking at a preview. This is the screen we just saw. It's on a new slide though, and it's got a table of values. So we'd love for students to make a connection between visually this graph and the values in this table to try to put together a function to go in down here. And they can then test themselves and get some great interpretive feedback and make their own adjustments. And this is a great part of mathematics where they can get feedback based on their own work and make adjustments to it. So let's say they do this correctly and they recognize that the equation or the function should be 600 minus 16x squared. When they press submit, the submit button is tied into this graph. Watch what happens. Now, this doesn't necessarily use the animation sync in this graph, but it's similarly related, all of these screens here. If the student were to type in something incorrect, for example, they had the wrong initial height, this is where great interpretive feedback can come into play. Clearly, the student sees it's not matching. They can make some adjustments. Okay. Likewise, if they have the correct initial height, but maybe they forgot to use the 1/2, you can see here it will fall more steeply. So how do we build this? I'm going to leave preview mode and show you what's on this particular screen. There's a table with values that I filled in, nothing more, no computation layer there. There's a note with directions for the students, nothing fancy there. There's a math input box. There is some computation layer here. I just wanted to prompt them with f of x equals so that they're using function notation, nothing more than that. But I'm calling it input. And that input is important because we're going to tie it into something over here. We're going to use the simple function concept to define function f, which has been done many times before. Many of you are familiar with that. We're also going to define the number t sub 0 as coming from that input button, and its source is going to be time since submit. Now we're going to let it run for 6.124 seconds. At this point, hopefully you remember that the purpose of the 6.124 seconds is that's how long I know it's going to be in the air. So I'm going to let this run for that amount of time. In the component itself, similar stuff to what I had before. You can see all these points here. Those are all the same. I have added a new color, okay? And I added a new color because I wanted it to stand out when it traces this graph. So I added a new color in this manner. RGB is red, green, blue. And I've got another video out on this a little bit, but I wanted to have this lighter blue color. And then up here, this is the new part. I'm going to also graph y equals f of x. Well, right now, Desmos can't graph that. It doesn't know what f is. F's not defined. It's defined in the computation layer once the student submits something. So let's go ahead and see it again in preview mode. Student types in 600 minus 16x squared. It activates our timer. And there's that color blue I wanted to see, and I made it a lot thicker so it would stand out a little bit. So hopefully some of this was useful or helpful for you. I just think this animation feature is really great with motion situations, and I look forward to playing around with it. Thanks.